Hello all, welcome to the class of Discrete Mathematical Structures 18 CS Prefix. Today I'll be teaching a topic in Module 5, Trees. The topic name is Prefix Codes and Weighted Trees. Myself, Dr. Madhura, working as an assistant professor in the Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. First, let us understand the definition for binary sequence. A sequence consisting of only zeros and ones is called a binary sequence or a binary string. So any sequence that consists of only zeros and ones is called a binary sequence. Alternately, it is also known as binary string. The number of elements contained in a sequence is called its length. So in a binary sequence, the number of elements which is full of zeros and ones, the number of elements that it is contained in a sequence will be given by the length. So if at all we want to find the length of a binary sequence, that can be found out by counting the number of elements in it. So some of the examples of binary sequences are taken here: 0 1, 0 0 1, 1 0 1, 1 1 0 0 1, etc. These are the binary sequences of lengths respectively 2, 3, 3, 5, 7. So there are only two elements in the first one. In 0 1 there are only two elements. So the length of this binary sequence is 2. In 0 0 1 there are three elements. So length of this binary sequence is 3. Similarly for 101, 11001, etc. So length of the binary sequences can be found out by counting the number of elements in that sequence. Prefix codes. Let P be a set of binary sequences that represent a set of symbols. Then P is called a prefix code if no sequence in P is a prefix of any other sequence in P. So we consider a set of binary sequences denoted by P, which represents a set of symbols for us, consisting of only zeros and ones. We say that P is a prefix code if no sequence in P is a prefix of any other sequence in P. Say for example, we can observe P here: 1 0 0, 1 1 0 1, 1 1 1, 1 1 0 0. These are a set of binary sequences which is denoted by the set P for us. And we observe that none of the sequences are prefixed to any other sequence. So what we mean to say is 1 0 should not be a prefix of any other sequence. Similarly, 0 should not be a prefix of any other sequence, etc. In the same manner, we observe another set, say Q equal to 0 0 0, 0 0 1, 0 1, 1 0, 1 1. So, none of these should be a prefix to any other sequences in the same set. So, these are the prefix codes for us. Whereas we observe that set A and B are not prefix codes. Why is it not prefix code? Let us observe and understand. So we observe 0 here. This is one of the sequence, one of the binary sequence, and this is regarded as a prefix to another sequence. So 0, 1 you can observe here. So this is treated as a prefix to some other sequence. Similarly, if we can observe, we have 1 here as another sequence. This is a prefix to another sequence, say 1 0. Like that, we can observe or have many other sequences being prefixed to any other sequence. So A is not a prefix code. Similarly, B is not a prefix code because 0 0 is a prefix to another prefix, another sequence 0 0 0. Or 0 0 0 is a prefix to another sequence 0 0 0 1. So that is the reason B is not a prefix code. Next, prefix codes can be represented as binary tree by constructing a full binary tree of height equal to length of longest sequence in the code and assign symbol 0 to every edge that is directed towards the child in the left from its parent, and symbol 1 to every child that is directed towards the child in the right. So we can assign zeros and ones for all these in the form of a binary tree represented. So the prefix code firstly can be represented in the form of a binary tree, and we can hence construct a full binary tree of height equal to the longest sequence in the code. And we assign zeros to the left child and ones to the right child. Next, we will understand the definition for weighted trees. Consider a set of positive integers w1, w2, w3, etc. up to wn, where w1 is less than or equal to w2, w2 is less than or equal to w3, etc. up to wn. Suppose we assign these integers to the n leaves. Means we are trying to put these integers w1 to wn to the n leaves that are existing in the complete binary tree T in any one-to-one manner. Then the resulting tree is called a complete weighted binary tree with w1, w2, w3, etc. up to wn as its weights. So the weights of the trees can be given. We are giving the weights to the trees means we are giving the weights to the leaves, n leaves that are existing in the complete binary tree T. So we assign weights to the leaves, and such a tree will be known as complete binary tree, complete weighted binary tree with w1 to wn as its weights. Suppose L of Wi denotes the level number of the leaf to which weight Wi is assigned. So we denote the level number. Once the weights are assigned to the leaves of the tree, we can denote or write down the level number of that particular weights. So which is denoted by L of Wi. Then W of t gives us the weight of the tree defined by W of t equal to summation I equal to 1 to n Wi into L of Wi. Wi gives us the weights of the leaves multiplied by its level number. Multiplied by the level number gives us L of Wi. So this we are taking summation over I equal to 1 to n. Means for every leaf we will be able to do this, and we sum up all of them to get the weight of the tree. Wi into L of Wi. Weights of the leaves multiplied by its level number. We are going to sum up for each one of them, which gives the weight of the tree. Next, optimal tree. Given a set of weights, consider the set of all complete binary trees to whose leaves these weights are assigned. A tree in this set which carries the minimum weight is called an optimal tree for the weights. So we are given with a set of weights, and we consider the set of all complete binary trees to whose leaves these weights will be assigned. And a tree in this set which carries the minimum weight will be known as the optimal tree. So given a set of weights and we have a set of complete binary trees being drawn for which the weights are assigned for the leaves of those complete binary trees, and among all those trees one of the tree will have the minimum weight, and by calculating the minimum weight, whichever the tree complete binary tree has a minimum weight, such a tree will be known as optimal tree. Optimal tree for the given weights. For a given set of weights, there can be more than one optimal tree. So remember that for a given set of weights, we need not have a unique optimal tree. There can be more than one optimal tree. Huffman's procedure. Let us understand what do we do exactly in Huffman's procedure. An optimal tree for a given set of weights can be constructed as follows. So in order to draw an optimal tree, that is which carries a minimum weight, so in order to draw that optimal tree with a given set of weights, we use the Huffman procedure. So the procedure is as below. We arrange the weights in non-decreasing order first and assign them to isolated labeled vertices. A set of weights would have been given to us. We first arrange those weights in non-decreasing order. Means from lowest to highest we are going to arrange them, and we assign these weights to the isolated labeled vertices. So we take a set of vertices and we are going to assign those weights to those vertices and we are going to label them. We select two vertices with minimum weights, add these vertices to get a new vertex, draw a tree with new vertex as the root and the selected vertices as children. We leave the remaining vertices undisturbed. So we take the minimum of those two weights, we add up them and we try to form a tree. We add up those two minimum weights, they become the leaves and you join them by edges and make a tree. We form a tree whose parent will be a new vertex for us, which is denoted as a root, and we selected the selected vertices will become the children. The minimum two vertices weights that we considered, no, they become the children, and through which if you draw a edge and make a parent, that parent becomes a root. So we leave the remaining vertices undisturbed. We repeat this process or this procedure in step 2 whatever we did until all the vertices and the subtrees are connected to get a single complete weighted binary tree. So the same procedure again and again we consider the two minimum weights and we add up them, we combine them through a tree, we form a root, and we'll have a set of small trees for us, or a set of sub trees will be carried. All that together when we keep connecting once we will get a complete binary weighted tree. So the tree obtained is known as the optimal tree for the given set of weights, and this is known as the Huffman's tree. And remember, this tree is not unique. So the tree obtained by following the above procedure is known as the optimal tree for the given set of weights and is known as Huffman's tree also. This tree is not unique. Given a set of weights, weights might be repeated. So whenever we have repeated weights and all, we will obviously not get a unique tree. So that was your Huffman procedure. Now moving ahead, we have optimal prefix code. So obtaining an optimal tree, we will be able to write down the optimal prefix code for the given message. So let us see how is that. Huffman's tree or the optimal tree can be used to obtain a prefix code for the symbols representing its leaves. We write down the Huffman tree or the optimal tree, and this can be used to obtain the prefix code for the symbols representing its leaves. For this purpose, we first label the symbols 0 and 1 to its edges by labeling procedure which we learned earlier. The labeling procedure means we assign 0 to the left child and we assign 1 to the right child. So the edges that are carried will have zeros towards the left and 1 towards the right. Then all the vertices and the leaves of tree can be identified by binary sequences. All the trees and the leaves can be identified by the binary sequences, and those binary sequences through which the leaves are identified yield a prefix code for the symbols representing the leaves. This prefix code is known as optimal prefix code. This prefix code, what we obtain, is known as the optimal prefix code since we have obtained it from the optimal tree. So obtaining the optimal tree by the Huffman procedure, we assign zeros and ones by labeling procedure, followed by we will be able to write down the code for each of the symbols given in the question, through which we will be able to obtain an optimal prefix code. And again, as the optimal tree is not unique, the optimal prefix code will also be not unique. Now, we will take up with the problems based on the prefix codes and the weighted trees. Firstly, Construct an optimal tree for a given set of weights. So the given set of weights are 4, 15, 25, 5, 8, 16, and hence we need to find the weight of the optimal tree. So first we need to construct the optimal tree by Huffman procedure and hence find out the weight of the optimal tree. So let us see how to do. Solution. Arranging the given weights in non-descending order first, and we associate the vertices A, B, C, D, E, F for each of these weights. So we have the step 1, the isolated vertices we have considered because there are 6 weights given for us, 4, 15, 25, 5, 8, 16. There are 6 weights totally given for us. So we have 6 weights considered, and each one of them we label it by A, B, C, D, E, F, and we are arranging this in the non-descending order. So in the increasing order, starting from the least weight, we are arranging this. So within brackets, whatever is written are nothing but the weights of those isolated vertices. So A carries the weight 4, B has the weight 5, C has the weight 8, D with the weight 15, E with the weight 16, and finally F with the weight 25. Now according to Huffman procedure, we apply we add up minimum of the two weights. So 4 and 5 are the minimum of the two weights. We add up these two and create a tree. We prepare a tree. These two A and B vertices become the children, and there exists a root or the parent of A and B, which we call it as a new vertex, say V1. So that can be observed here. We have the next least vertex, that is C, as it is in its place. We have 4 plus 5, which is equal to 9. The weight of these two isolated vertices are 4 plus 5, 4 and 5. 4 and 5 added together gives us 9. So we are placing that new vertex V1 after, after the vertex C, which is carrying the weight 8. So after C, we have to place the new vertex because its weight is higher than the original vertex, that is C. So V1 has the weight 9. Its children are A and B. Its children are A and B. The remaining vertices D, E, F are also kept undisturbed. C comes to the beginning because it has the weight 8, which is lesser than the new vertex weight, that is V1 vertex weight 9. So that is the reason we place vertex C at the first place and then followed by the new vertex or the new root V1, whose children will be 4, A and B. In step 3, again we consider the minimum of the two weights. Now the minimum of the two weights is 8 and 9. That is C and V1 carries the minimum weights. So 8 plus 9 gives us 17. So the new vertex V2 has children C and V1. The left child will be C, right child will be V1. And that new vertex will be placed after E because it has the weight 17. 15, 16 weights will be kept as it is. Then followed by the new vertex V2 with the weight 17. Then the undisturbed vertex, that is F, as it is. So that is what we can see in the step 3 now. D and E are undisturbed. They have the weight 15 and 16. Now comes the new vertex V2, whose weight is 17. Its children are C and V1. And V1 already had two children, A and B. Again, keep the undisturbed vertex F as it is. This was our step 3. Again, now moving ahead, adding up the least of the two vertices, that is D and E can be added. These two have minimum weights. So 15 plus 16 gives us 31. So with these two as the children, we form a tree. The new vertex will be named as V3, whose weight is 31. So that will be placed at the last after 25. Every time we take care that we are arranging in the non-decreasing order. So step 4, We have this undisturbed vertex along with its children. There is this subtree written as it is. So V2 and their children C and V1 as it is. V1 children are A and B as it is. The undisturbed vertex F is also kept as it is. Now these two weights are added. 15 plus 16 is 31. So the new vertex V3 has the weight 31. Its children are D and E. So which has the weight 15 and 16. Next, we will go to the step 5 by again adding the same procedure. So we have the new vertex V3, just now what we obtained with the weight 31 written as it is, its children D and E retained as it is. Now the next new vertex formed is V4 with the weight 42, whose children will be V2 and F. V2 and V1 already have children, we retain them as it is. So that we have two subtrees now, and one last step, that is step 6, gives us the optimal tree because we will be combining these two trees. This has weight 31 and the new vertex V4 has weight 42. So we combine 42 and 31, gives us the following tree. The new vertex is V5 with the weight 73. The left child will be V3 and its children D and E as it is towards the left side, and towards the right side V4 with its children and sub-children in the same manner. So this is your optimal tree. Thus, now we will be able to write down the weight of the tree. So weight of the tree is given by, this is with respect to the vertices we have done. So the leaves that are there, A, B, C. Weight of the tree formula says that summation Wi into L of Wi. So Wi is nothing but the weight of the vertex multiplied by its level number. Weight of the leaf multiplied by its level number. We find out the weight of the tree only for the leaves. So I'll just go back and show it to you. We observe that A, B, C, D, E, F are the leaves of the tree, of the optimal tree. And they were the given isolated vertices, what we started in the step 1. So A, B, C, D, E, F are the isolated vertices, what we started with the beginning of the optimal tree construction. So these becomes the leaves for us. A, B, C, D, E, F becomes the leaves of the optimal tree. Their weights are given in the brackets. So while finding the weight of the tree, we will be multiplying the weights into its level number. So let us understand the level number of these leaves first. V5 is the root here, which is always at the 0th level. V3 and V4 are in the first level. D, E, V2, F are in the second level. C and V1 are in the third level. And A and B are in the fourth level. So every vertex weight, leaves weight multiplied by its level number gives us the weight of the tree by adding up all of them. So we observe for the leaf A, it has weight 4 multiplied by its level number means it is at the fourth level. So 4 into 4. The vertex B has weight 5. This is also in the fourth level. So 5 into 4. The vertex C is in the third level. It has weight 8. So 8 into 3. We have to sum up all these. Vertex D is in the second level. It has weight 15. So 15 into 2. Vertex E is in the second level. It has weight 16. So 16 into 2. Similarly for the vertex F, which is also in the second level, having the weight 25. So 25 into 2. So that is how we are writing for these vertices A, B, C, D, E, F. We write down the weights multiplied by its level number only for the leaves. Only for the leaves. And those leaves becomes the given original isolated vertices. So summing up all these, weight of the tree is 172 for the given data. So this is how we can find out weight of a optimal tree. First, we are going to construct the optimal tree by the Huffman procedure, followed by we can find out the weight of the tree by the formula summation Wi into L of Wi. We'll see the next problem now. Construct an optimal prefix code for the symbols A, O, Q, U, Y, Z that occur with the frequencies 20, 28, 4, 17, 12, 7 respectively. So the symbols are already given for us, which are A, O, Q, U, Y, Z, and their respective weights are given. And those weight itself we are here calling as frequencies. We have to obtain the optimal prefix code. So before we find out the optimal prefix code, we have to construct the optimal tree for the same. Optimal weighted tree. We have to construct first. So these symbols along with their weights are assumed as the isolated vertices first. And we arrange them in non-decreasing order. So we first arrange these symbols along with their frequencies in non-decreasing order, and we treat the frequencies as the weights and the corresponding symbols as the isolated vertices. And we will be able to write on step 1 in this way. So we had 6 isolated vertices in the given data. We write down the 6 isolated vertices and arrange them in the non-descending order. So least weight is for Q, which is 4. Then comes 7 with the symbol Z. Then comes Y with the symbol 12. Similarly, U, A and O. Again, we follow the Huffman procedure. We add the minimum of the two weights, that is 4 and 7 can be added. We add the minimum of the two weights, which forms a new tree. 7 plus 4 is 11. So we retain it in the beginning only. We have to arrange the new vertex with the along with the existing one again in the non-descending order. So V1 with the weight 11 has children Q and Z. Next, remaining symbols Y, U, A, O are retained undisturbed. We have step 3. Again we add up the minimum of the weights. Now the minimum of the weights is 11 and 12. 12 plus 11 is 23. 23, the new vertex V2 can be placed after 20. We have to arrange every time in the non-descending order. So we write down vertices U and A as it is with their weights. Then we place the new vertex V2 with its children V1 and Y and the subchildren. And we retain O also undisturbed as it is. So that is under step 3 for us. So this is how we get the next subtrees. Again, minimum of the two weights is U and A carrying the minimum weight 20 plus 17, which is 37. So 37 can be placed at the end because it has the highest weight than the existing one. So we will place the new vertex with weight 37 at the end. So this is how we can construct. We retain V2 with its children and the grandchildren as it is. Then we place the vertex O in the place as it is. The new vertex will be V3 whose weight is 37. By adding 17 and 20 we got 37. So its children are U and A as it is. We are constructing the subtree by joining them through a edge whose parent will be the new vertex V3. Again, minimum of the two weights is 23 and 28. We add up these two. 23 and 28 gives us 51, which is greater than 37, the existing root. So we place it at the end. That is in step 5. So V3 and its children are kept as it is. The new vertex V4 with the weight 51 has the children V2 and O, followed by V1 and Y as the children of V2, and then V1 has the children Q and Z. Again, The one final optimal tree can be obtained by adding up 37 and 51, which creates a new vertex as a parent, that is V5. With the sum of these two, which gives us 88. So we have V5 with the weight 88, followed by its children V3, V4, and the grandchildren as it is. So this is our optimal tree. Now we need to obtain the optimal, we have obtained the optimal tree or the Huffman tree. First, we are going to now assign zeros and ones to the edges using the labeling procedure. So we have these isolated vertices, which we started with in the step 1, being the leaves U, A, Q, Z, Y, O. These are the leaves for us now, which are the given vertices. We assign 0 to the left child and 1 to the right child. So every time we assign zeros and ones to the left and the right child respectively. So this is how we assign using the labeling procedure. Now we will be able to write down the optimal prefix code for the given symbols. So let us write down the code for A first. A has the code starting from the root. You are going to read the code always. So it is 0 and then 1. It is tracing or traversing the path 0, 1. So that is why A has the code 0, 1. Next, moving ahead to O. O has the code 1, 1. It is traversing starting from the root 1, 1. Next, for the symbol Q, we can write on the code as 1, 0, 0, 0. Q is at the third level, fourth level, I'm sorry. So Z always root is in the 0th level. So we have these two vertices in the first level, U, A, and this vertex and O in the second level. Y and the other vertex is in the third level. Q and Z are in the fourth level. That is why there are 4 symbols in this, right? So Q is traversed all the way from root with the symbol 1, 0, 0, 0. Next, we have U, Y, and Z in the same manner written. U has the code 0, 0. Y takes the code 1, 0, 1. Z has the code 1, 0, 0, 1. So this is how we will be able to write down optimal prefix code for the given symbols using the Huffman procedure. We have followed Huffman procedure to write down the optimal tree or the Huffman tree, and using the labeling procedure, that is assigning 0 to the left child and 1 to the right child, we will be able to write down the binary sequence or the optimal prefix code for the given symbols. We'll see the next problem. To obtain optimal prefix code for the letters of the word engineering, we hence have to indicate the code. So engineering is a message for us or a word for us given. For this, we have to first consider the letters and its frequencies. Frequencies, when we say, we just look into E occurring how many times in the word. N is occurring how many times in the given word. Similarly, G is occurring how many times in the given word. I is occurring how many times in the given word, etc. So we first have to write down its frequencies, then followed by the optimal tree and hence the code. So given word consists of the letters, which are the distinct letters that are existing, we are writing here. So E, N, G, I, R. These are the different letters that are existing and they have the frequencies 3, 3, 2, 2, 1 respectively. Means E is occurring 3 times. We can see E occurring 3 times in the word. N is occurring 3 times. N here, and then at the end here. We have G occurring 2 times in the word engineering, and we have I occurring 2 times. Finally, the letter R is also occurring 1 time. So we know the frequencies now. These frequencies become the weights of the isolated vertices later. We arrange these letters along with the frequencies in non-descending order. We treat the frequencies as the weights and the corresponding letters as the isolated vertices. So now comes the usual procedure for us. We have 5 distinct letters E, N, G, I, R. So we denote them by isolated vertices. We are arranging them in the non-descending order. So we have frequency 1 first, followed by G, I, E, N. Now it is not a compulsion that I have to take G first and then only I. Here, both G and I have the same frequencies. So if we want to write down I first, we can write down and G next. So that is how the optimal tree varies. Writing down varies from person to person. And hence the optimal tree will not be a unique one. And still, since the optimal tree is not unique, you cannot have a unique answer for optimal prefix code. Again, here you can observe E and N having the same weights. So it depends whether you want to write down E first or N first. Whichever you write down is also correct because they both have the same frequency or weight. We just have to take care that we are arranging them in the non-descending order. Now minimum of the two weights R and G adding up together 2 plus 1 is 3. We place the new vertex 3 at the end. Again, it is not a compulsion that you have to place it at the end only. We can as well place it before this N or before E because they all have the same weights 3. So the undisturbed vertices are I, E and N. I retained I, E and N as it is, followed by the new vertex V1 with the weight 3, whose children are R and G. Then we have step 3, again adding the minimum of the two weights, we obtain this. V2 has the weight 5, whose children are I and E. The undisturbed vertices are N, V1 with its children R and G. We have step 4, adding the minimum two weights again. 3 and 3 is added. 3 plus 3 is 6. We have to place this after V2. So V2 is undisturbed, kept as it is. V3 with the new weight 6. His children are N and V1. V1 has the children R and G. V2 is undisturbed. Now one last step. We need to combine these two trees. The minimum of the two weights are existing are 5 and 6, whose sum is 11. So we add up together and form a new tree with the new vertex V4 having the weight 11 with its children and the grandchildren in the same manner what we did. So this is your optimal tree. Once you have combined all the subtrees, we will obtain the one single tree, which is known as the optimal tree. We have followed here Huffman procedure. So this tree can also be called as Huffman tree. Now we assign zeros and ones to the edges using the labeling procedure. So 0 to the left child and 1 to the right child. Every left edge has assigned 0. Every right edge is assigned 1. That is the labeling procedure for this. Now the code for the letters or the symbols involved in the given word, that is in the leaves of the optimal tree is, we can write on the code now for all the leaves of the optimal tree, which are there in the given word. The word engineering has the letters E, N, G, I, R. So they are nothing but the leaves if you can observe, and all the new other vertices V1, V2, V3, V4, we are not writing the code for them. So we have E equal to 0, 1. E starting from the root you have to trace and write on the code always. So V4 is the root now, the final optimal tree. So starting from V4 it is traversing 0 and 1. So E get code it will be 0, 1. Then N takes the code 1, 0, 1, 0. G has the code 1, 1, 1. It is traversing entirely towards right side, so it is 1, 1, 1. I has the code 0, 0, 0, 0, entirely towards the left. R has the code 1, 1, 0. So this is how we have written the code for the letters of the given word. Now we need to write down the code for the word engineering. Engineering is the given word or the given message for us. So for this word, we have to write out the code. So it is E first, so 0, 1. N, so 1, 0. G, so 1, 1, 1. I, so 0, 0. Again N, so 1, 0. E, so 0, 1. And again 0, 1. Followed by R, E, E. So followed by R, then R has the code 110, etc. So we just club all of these according to the given word letters. Engineering, according to these letters, we are going to write down the code. And there is no space, anything here. So that is why you have to continuously write down the code. So this is how for a given word, we will be able to write down the prefix code, optimal prefix code. We'll see one last problem. To write down the optimal prefix code for the message, road is good. So a message is being given to you. For this message, we have to write down the optimal prefix code, and finally we need to indicate the code for the given message. So let's see the solution. The given message consists of the letters R, O, A, D, I, S, G. These are the different letters that are existing in the given word. We have R, we have O, we have A, D, and then I, S, and G. The remaining are repeated here. And they have the frequencies 1, 3, 1, 2, 1, 1, 1 respectively. Means how many times that letter is existing in the word gives us the frequency. So R is existing one time in the given word. O exists 3 times. O is occurring 3 times in the given word. So 3. Similarly, A is occurring one time in the given message. So it is one frequency. Similarly, D is occurring 2 times. Road, good. In this D we have 2 times. So 2, etc. Along with these letters, we also see space between these words, no? After road, we have a space. After the word is, there is a space. So we need to consider the space also. So there are 2 blank spaces. So even this is one of the symbol what we need to consider, which is occurring 2 times. So space has the frequency 2. So we have to arrange these letters in these symbols, including the blank space, along with their frequencies in non-descending order, treating the frequencies as the weights and the corresponding symbol as the isolated vertices. How our usual procedure starts, that is, we denote the isolated vertices, we arrange the weights of these or the frequencies what we obtain for these letters along with the space that is existing in the given message. For that entire thing, we have to write down in terms of the isolated vertices carrying with the minimum weight in the non-descending order. So step 1, we have 3, 4, 5, 6, 7, 8. 8 isolated vertices because R, O, A, D, I, S, G and include space later. So totally 7 symbols. We arrange them in non-descending order. So this is how we can have R, A, I, S, G has weight 1. I took R first, followed by A, I next, followed by S, and then followed by G. It is not a compulsion that you have to take R first and then A, I next like that. If we are shuffling this, obviously we will get a different tree. So it depends on how the way we consider to get the optimal tree. Hence the optimal tree is not unique. That is the reason optimal code is also not unique. Then D and space has the weight 2. The letters D and space has the weight 2. So we have written next in the non-descending order, followed by O, which has weight 3. Now the minimum of the 2 weights is R and A. 1 plus 1 gives us 2. So we add them and we form a tree. I have taken 2 at the end before O. For the vertex O I have taken. So it is up to you where you want to place the new vertex B1 with the weight 2. You can as well place it before D or after D. The choice is yours. So 2, 2, 2. The weights are same, so they all have to be together. You are placing this V1 before D is also okay. Or if you are placing V1 after the symbol D and between D and space also is okay. I have put it at the last, just before the next new weight, that is 3. Again, minimum of the 2 weights is I and S. 1 plus 1 is 2. I place it after V1, which you can see it in the step 3. So this is how the new step is formed. So we have G, D and space undisturbed along with their weights. V1 already had children A, R and A. We have retained it as it is. Now the new vertex is V2 with its weight 2, whose children are I and S. The undisturbed vertex O is also retained as it is. Next we have minimum of the two weights is 1 and 2, that is G and D. Adding together, the new vertex weight is 3. We place that new vertex after O. You can as well place before O. I have placed it after O. So this is how the next step 4 can be written. The new vertex V3 with the weight 3 is written, whose children are G and D. The remaining all other vertices and its children are undisturbed. Again, space and V1 should be added. These are the minimum two weights to add now. So space is having the weight 2, V1 is having the weight 2. So these two added together gives us the new weight as 4, obviously to be placed after V3 at the end, because it is the highest weight of the root that we have now. So we have to place it at the end only. Remaining all other vertices and its children will be undisturbed. So this is a new tree formed. New vertex V4 whose weight is 4. The left child is space and the right child is V1. V1 has two children R and A. So remaining vertex is V2 and its children O, V3 and its children are undisturbed. Now again the minimum of the two weights is V2 and O. V2 and O has weights 2 and 3. Adding up together the new weight is 5. We have to place that new vertex V5 with the weight 5 at the end because it has the highest weight compared to all others. So we place it at the end. That's in step 6 we can see. New V5 is the new vertex with the weight 5. Its children are V2 and O and V2 has the children IS. And we have V3 undisturbed, V4 and its children and the grandchildren undisturbed. Step 7. So again and again we observe we are implementing the Huffman procedure, that is adding up minimum of the two weights and putting it in a proper place according to non-descending order every time. Now the minimum of the two weights is V3 and V4. V3 has the weight 3, V4 has the weight 4. Adding up these two weights we get 7. So new vertex V6 with children V3 and V4 has the weight 7. So it should be placed at the last. So we retain V5 with its children and grandchildren as it is, undisturbed. So V6 is the new vertex whose weight is 7. Its left child is V3, right child is V4. Whatever the left subtree is there, we try to retain it there only, and whatever the right tree is there, subtree is there, we retain it to the right side. V3 has already the children GD, V4 has children space V1, V1 has children RE, everything as it is. V5 with its children and grandchildren are kept as it is, undisturbed. Now one last step. By combining these two subtrees, we will be able to join them by edges. V5 with the weight 5 and V6 with the weight 7 are added. So 7 plus 5 gives us 12. 12. So the new tree, optimal tree, has the weight V7 as a new vertex with its weight 12. And the children and the sub-children are written in our usual procedure. This is the optimal tree for us. Now, let us assign zeros and ones. We are assigning zeros and ones in the labeling procedure according to that. So 0 to the left child and 1 to the right child. For every left and the right child, we are assigning zeros and ones for the edges. Now, code for the symbols, that is the leaves of the optimal tree. The symbols in the given message was ROAD space G, and then we also had IS. So only for those symbols we are going to write down the code. So let us write down the code first, followed by code for the given message. So we have R symbolically, it is 1110. R is at the fourth level. So it is traversing all the way from the root. Root here is V7. So traversing from the root, it is passing 1110. Then we have the symbol O. O has the code 01, followed by A. A has the code 1111. D has the code 101. Similarly for the remaining vertices. Space. For space also we can write on here 110 is the code for the space. Now we will write down the code for the message road is good. Including the space we have to write down. We will not only write down code for ROAD without any spaces. We also have to write down the code for a space that is existing in the given message. There are two spaces existing in the given message. No, for that we have to write down the code as 110 what we obtained. Remember, the optimal tree is not unique. Based on how the way you would have written the weights, you would have got the optimal tree. So since optimal tree is not unique, optimal code also will not be a unique one. So this is the code for the given message, that is road is good. So this is how we work out problems on prefix codes and weighted trees. For a better clarifications, you are given with practice questions. So you can just practice these questions and try to obtain the optimal tree followed by the prefix code. Thank you for watching.